Alrighty, howdy folks. Uh, Section 4 of Chapter 16, and this is about something called Greens Theorem. Oh boy, this is a pretty important one. One thing I need to tell you, the moment you see a theorem with a name attached to it, it could be the name of an individual, or it could be a generic name like mean value theorem, fundamental theorem of calculus, something like that. They tend to be incredibly important. And Green's theorem, by the same logic, is a very important one. And the question is, what's the big deal about it, right? And so what I thought I would do is I'll give you a motivation as to uh, why we need to learn about Green's theorem, okay? Here is the idea. Green's theorem gives the relationship between a line integral around a simple closed curve C and a double integral over the plane region D bounded by C, right? I don't know what that means, man. Yeah, I agree. So let me try to explain. In the previous section, we learned about line integrals or contour integrals or line integrals, right? But in the specific case where that contour or line is actually a closed curve, like what we see here, could we find the line integral? Yeah. Wait. Wasn't the closed integral in the closed integral around a closed contour, wasn't that automatically zero? No, that is zero only if the field is conservative. Okay, if not, then that statement is not true. In general, integrating over a closed curve doesn't give you necessarily a zero. Okay, so okay, now what Green's theorem does is, hey, guess what? If you want to evaluate the integral around this on this line integral, closed line integral, it's exactly the same as finding, I don't need that right now, finding the integral over the area that this thing covers. We dealt with double integrals over some area, right? Now, this line integral is exactly the same as if you were to evaluate that quantity inside this area that is covered by this closed loop. So that's a very powerful thing. And what I'll try to show is, for a particular integral, we will figure out both ways and show that you get the same answer regardless. So what that means is, depending on the situation, depending on what the contour integral looks like, what the contour or the curve looks like, you may want to resort to one technique or the other. Okay, you may want to evaluate it as a double integral over a region, as opposed to evaluating the contour integral. So that's the key. And for this, one of the terminologies that you need to become familiar with is, what is a positive orientation of a closed curve and what's a negative orientation of a curve. And that is important to know because in some cases, if the curve is oriented in a negative, then the integral is actually negative of the positive version. I'll explain all of that in just a second. Okay, so here, notice the contour is actually has a direction and it's going counterclockwise. If you have an XY plane, that is considered to be positive orientation if it is counterclockwise. Okay. On the other hand, if we were to have clockwise orientation of this curve, then that's a negative orientation. Cool. I'm not going to say much more about it right now, but when we get to a particular problem, I will invoke this concept. Okay, counterclockwise. The way you need to read this is I don't know how many times you have seen this, but people in the business tend to write like this in order to be brief. The way you read this is a counterclockwise orientation is considered positive. Okay. A clockwise, the stuff in the parentheses, a clockwise orientation is considered negative. So that's how you're supposed to read. Don't be confused by, what the heck, man, a counterclockwise and clockwise? Counterclockwise is different from clockwise, right? And positive is different from negative, right? Yeah, you're right. However, you're supposed to read this like that, okay? All right. What else? Now let's get to what in the world this Greens theorem is about. Let C be a positively oriented. So we are invoking what positive oriented is from the previous slide. Positively oriented, piecewise smooth. Ooh, piecewise smooth. And this smooth means derivatives are nice and continuous. If it so happens that in different intervals, it's piecewise smooth in different intervals, that's okay. It doesn't have to be smooth all over, but we are not going to bump into those kind of things. Once you go into advanced calculus, that's where piecewise smooth and all kinds of things like that become that much more important. But in our case, pretty much everything is a smooth curve. Okay. Simple closed curve. So it has to be positively oriented, piecewise smooth, and a simple closed curve like the one that we saw in the previous slide in the plane, and let D be the region bounded by C, right? Just like in the previous slide. Then here is the key. If P and Q have continuous partial derivatives on an open region that contains D, okay, then this vector field F dotted with dr, the integral on this, the contour integral F dot dr, F is a vector field, and dr, R is the parametric form of the curve. That integral is nothing but integral of P dx plus Q dy. What is this P and Q? Well, we are saying that F is nothing but P dx, P of x, F is nothing but Pi plus Qj. Let me repeat that. This F, vector field F, is P of xy I plus Q of xy j. So that means it's a vector whose x and y components are P and Q. Okay, so we have shown that in fact this contour integral F dot dr is nothing but P dx plus Q dy. And we can write this as like this, or we can write this as because the contour is closed, we can write it as a closed integral like that. Okay, P dx plus Q dy. And here is the money statement. The Greens theorem has shown that, well, in order to evaluate this contour integral, if you know that F as some Pi plus Qj, guess what? All you need to do is evaluate the area integral of this quantity, partial Q with respect to x minus partial P with respect to y. The proof of this is pretty complicated, the general proof. So if those of you who are interested in proofs, you may want to look at the textbook. I'm not going to go through it. Even the book says this is pretty complicated and shows only for some simple cases how this works. All right. And as if most of you are engineers, the proof of the Greens theorem is not as vital to us, especially not in an undergrad class. Okay. All right. So keep this in mind. if f is pi plus qj, the vector field f, and you want to evaluate this on a contour, evaluate the integral on a contour given by r, vector r, then all you need to do is evaluate the area integral, the double integral over that domain. This C is covering up a whole area D, and so partial q with respect to x minus partial p with respect to y dA. If you did that, you got the answer to this. Vice versa. Okay, that's the key. Note that here is C. Here C is a closed curve, right? I talked about that. Like I was mentioning, well, closed integrals, shouldn't the integral be equal to 0 as we saw in the previous section? Like I said, no. That's only true if f is conservative. That vector field is conservative. If it is not, then that statement is not true. Okay? All right. So let's go ahead and talk about a certain problem. Pick up a problem. Evaluate the line integral by two methods. One is directly, and the second one by using Greens theorem. Right? What a beautiful example to illustrate the concept. Obviously, here we have a line integral, contour integral, or line integral, and the curve itself happens to be, the contour happens to be a triangle with vertices located like this. Cool. So that's how the problem statement was. So I went ahead and said, okay, let me draw this just so that we can be clear about what the curve looks like. And one of the things that we have to do is notice they didn't say whether this contour is positively oriented or negatively oriented, right? Nobody mentioned that. And that's precisely why we would have to go, we would have to draw this and figure out whether or not the orientation is positive, which means we first pick point 0, 0, then find 1, 0 and 1, 2, and this order is important. The contour goes from 0, 0 to 1, 0, and from there to 1, 2, and then from there back to 0, 0, just like I have shown here. 0, 0 to 1, 0, 1, 0 to 1, 2, 1, 2, back to 0, 0. And when it does that, notice the orientation is definitely counterclockwise, which is positive. Okay? And I think in one of the problems that comes later, the orientation is negative, and I'll show you what the repercussions of that are. Okay? All right. Where are we? So we need to evaluate this by A, directly, and then by using Greens theorem. Okay. What's the direct method? Oh, well, it's a contour integral. So we need to split this into C1, C2, C3. So let's figure out what the curve C1 is in a parametric form, and similarly C2 and C3 first. Okay. All right. To me, whenever I have a line segment, this is my my go-to way of figuring out. What is that? The initial point is 0, 0, and the terminal point is 1, 0. Right? I take my initial point as a position vector and multiply that by 1 minus t plus the terminal point times t. Let me remind you quickly why that works. This clearly says if t were to be 0, let's see what happens. If t were to be 0, the second part just goes to 0, right? Okay, and what happens to the first part? 1 minus t becomes just 1. 1 times the initial point. Well, when t is 0, that means we have the initial point, and that's this guy. That seems to make sense. Likewise, when t happens to be 1, right? T is going from 0 to 1. When t happens to be 1, this quantity goes to 0, leaving us with 1 times just the terminal point. So when t was 0, we have the initial point, and t equals 1 corresponds to the terminal point. That's exactly what we want. So that's my go-to way of doing things. I must have talked about it in previous sections as well. Okay, cool. Let's do this. Does it become t comma 0? What did I do? I'm just looking at the x components and adding them up. Isn't that how we add vectors? Add the x components, comma, add the y components. 0 times 1 minus t is 0. 1 times t is t. So 0 plus t is t. That's the x component. Y components now. 0 times 1 minus t is 0. 0 times t is 0. So 0 plus 0 is the y component, 0. Right? So the r of t for C1, or 1 of t, maybe I should say that, is nothing but t comma 0. In other words, we can interpret this as x being equal to t and y being equal to 0. Cool? And absolutely vital is to recognize that t goes from 0 to 1 because of how we set this up. Okay, what else? Well, notice our integrand has x, y, dx and x square y cubed dy. So we are going to plug t for x and 0 for y, but then that raises the question, what are you going to plug for dx? And what are you going to plug for dy? So that means we really need to figure out dx and dy. So let's go ahead and do that. X is equal to t, so dx equals, simple, dt. Y equals 0, so dy equals 0, or if you want to call it 0 dt, right? That's exactly what I did. Basically, that is 0. Why'd you say 0 dt, man? I don't know. So 0 dt. Cool. C2, same idea. Initial point is 1, 0. Terminal point is 1, 2. So initial point times 1 minus t plus terminal point times t. 1 minus t, add the x components. 1 minus t is the x component in the first case. 1 minus t plus t. 1 minus t plus t just simply becomes 1. So x equals 1, or this x component is 1. Cool. 0 times 1 minus t is 0, plus 2 times t is 2t. 0 plus 2t is 2t. Right? Or x equals 1, y equals 2t. Again, t goes from 0 to 1. Let's figure out dx. What is dx? Derivative of 1 is just 0. So 0 dt. Okay, what's dy? Y is 2t. So 2 dt. Right? That's what I wrote. Similarly, for C3, the line segment from 1, 2 to 0, 0, initial point times 1 minus t, blah, blah. I did that same kind of a thing. All right. Now, if our objective is to evaluate this integral, that integral with the contour is actually made up of 3 different contours, or 3 different lines or curves. So we need to evaluate this quantity over the integrand over this first curve plus the second curve and the third curve. So what I figured I'd do is I'll just separate them. Whoa. I'm sorry. I goofed on the... Don't look at the bottom one. Okay, so let's look at the first one, C1. xy dx plus x square y cubed dy. Because we are changing the variable to t, so obviously 0 to 1, because for C1, 0 to t, 0 to 1 is how t is changing. Okay, and what else? X is t and y is 0. So would you agree? X times y would be t times 0, and dx is just dt, plus x square is t square, y cube is 0 cube, dy, maybe I should have said 0. I should have been more clear. Okay, let me fix both of them then. Come on. What is animations? 15 should not be 15. 15 should be 17. Okay, now it's going to show up at the right time. So let me change this to 0 dt. This is the kind of crap I have to go through every time I make a slide for you guys. It's a lot of work. But I think I want to do it because it is so much more efficient. I cannot imagine going back to the blackboard and writing, and me writing and you sitting there and copying it, and with my back turned to you. Yeah, I like this a lot better. Anyways, where are we? Cool. 0 dt. All right. So now, wait. So that is just 0, and this is also 0, and the whole integral is just 0. All right. That made life simple. Cool. Go to the second curve, xy dx. X is 1, y is 2t. Let's keep that in mind. X is 1, y is 2t, dx is 0 dt, dy is 2 dt. So 1 times 2t times 0 dt, 1 square, 2t the quantity cube times 2 dt. All of this, folks, if this integral goes to 0, what are we left with? The 2 cube is 8, 8 times 2 is 16, 16t cube dt. The integral of t cube is t to the 4 over 4, 16t to the 4 over 4. From 0 to 1, that's just going to be 4. Cool. Now, this other one, that seems to be pretty involved. X itself is 1 minus t, and y happens to be 2 times 1 minus t. And dx is negative dt, dy is negative 2 dt. So carefully, I did all of this. And then when you evaluate this, please take a piece of paper and write down all of these things and evaluate this integral. I'm just giving you the final result. It turns out to be negative 10/3. But you should be good boys and girls and verify that in fact it is correct. Okay, so what happens? This becomes 1 minus t the quantity square. So maybe use substitution. Similarly, this becomes 1 minus t the quantity to the 5 with some big constant. 2 cube is 8, 8 times 2 is 16, all kinds of things like that. Okay, evaluate that, and that turns out to be negative 10/3. Okay, what the hell are we supposed to find? Oh, we're supposed to find this contour integral, right? And we have found each individual component. The only thing we are left with is adding up each of these parts. 0 plus 4 plus negative 10/3, or 4 minus 10/3 is 2/3. And guess what? That's the integral. By what method? By the direct method. You have been given a contour integral, and you evaluated the contour integral by treating that as contours. Now the Greens theorem. Before I show you the Greens theorem, how are we supposed to interpret Greens theorem? Do I have it? Yeah, good. Greens theorem says, hey boys and girls, if you want to integrate, find a contour integral PD of PDX plus QDY, Wait, is that how ours is? Yeah, p dx, p of xy dx plus q of xy dy. Yep, that's exactly what we have. And this one says, if you want to do that, tell you what, you can do partial q with respect to x. So q is this guy, partial q with respect to x minus partial p with respect to y, which is xy. So take that and evaluate that on this area. What? I don't know how to evaluate. Well, you should, right? This is something that we did in the previous chapter. What type of integral is this? Well, should we integrate along x or should we integrate along y? The truth is it doesn't matter in this case. I think in this case I have chosen to draw a representative rectangle vertically, which means at the end I will integrate from x equals 0 to x equals 1 at the end. Okay, so we have p equals this, q equals this. For the area integral, we'll integrate from left to right, that is along the x direction. This means we have 0 less than or x less than or equal to 1, right? X goes from 0 to 1. And what does y go from? Well, in this type 1 integrals, you have to draw a vertical rectangle to indicate that you are moving along the x direction. When you do that, when you draw a vertical rectangle, the top portion of that rectangle is touching this curve. What's the equation of this curve? Y equals 2x. How do I know that? Well, that's a straight line segment. So it's got to be in the form of y equals mx plus b. And b, the y-intercept happens to be 0. It's passing through the origin, right? And m, what is the slope? Well, slope is rise over run. In this case, the rise is 2 units for a run of 1. So 2 divided by 1. So slope is 2, and therefore y equals 2x is the equation of the line. Why do we need to know that? Because we can say that y goes from 0 to 2x. And because we need to plug into this, I'm figuring out partial q with respect to x. Partial q with respect to x. Would you agree that is y cube is treated as a constant, so derivative of x squared is 2x, so it makes it 2x y cube. Similarly, partial p with respect to y, hold x as a constant, differentiate y, you get 1, x times 1, which is x. Simple? Yeah. So the next thing we need to do is, notice you have to integrate with respect to y first and then by x. Okay, so if you do that, I won't insult your intelligence. It's just a matter of plug and chug. I'll let you look at it more carefully. Eventually, it turns out to be 2/3. Wait, what were we supposed to do in this problem? We were supposed to evaluate this integral in 2 different ways. When we evaluated it by just the direct method, what did we get for the integral? 2/3. When we evaluated it by using the Greens theorem, what did we get? We better get the same thing, otherwise the theorem would be wrong. Well, an established theorem like that cannot be wrong. I can fairly confidently say that. The only thing is, if these 2 numbers did not come out to be the same, it is we who goofed it up. So we better look at our work. But anyway, so as expected, the 2 values turned out to be the same. Cool? All right, next. Use Greens theorem to evaluate the line integral along the given positively oriented curve. Oh, like that. Okay, what is that curve? It's the boundary of the region between the circles x square plus y square equals 4 and x square plus y square equals 9. Ha, whoa. Okay. Do we still have that same p of xy dx plus q of xy dy? Yeah, that part is the same. What's up with this contour? Well, I went ahead and drew it. So basically this is a circle with the radius 2 and center at the origin, and this is that one is center at the origin, and the radius is 3, and all are positively oriented curves. So we need, this is the area that's being bounded by the two curves, and we need to evaluate the so that's what the curve actually is. C is the boundary of the region between the circles. Ooh, it's an interesting one. Okay. Oh, fortunately, they said just go ahead and use the Greens theorem. So though we need to evaluate the line integral, thankfully Greens theorem allows us to find the area integral, which is relatively easier. So we'll do the same Greens theorem thing here. Evaluate the area integral partial q with respect to x minus partial p with respect to y. P happens to be 1 minus y cube. Q happens to be x cube plus e to the y square. Let's automatically, what that means is partial q with respect to x and partial p with respect to y is what we need to first find. And C, evaluate this over this, is nothing but evaluating the integral over the area. Okay, so partial q with respect to x is 3x square minus partial p with minus negative 3y square became 3y square. And now the question is, do we know how to evaluate this area integral? Right? Because this has radial symmetry, and also quite nicely 3 can be factored out and you get x square plus y square. It's crying out to have polar coordinates to be used. So we will evaluate this as with using polar coordinates. I yanked out a 3, and x square plus y square in polar is r square. dA, remember you cannot say dr d theta. dA is r dr d theta. And so far as the limits on r and theta are concerned, the r limits are 2 to 3. What? Yeah, right? The inner radius is 2 units and the outer radius is 3 units. So that's exactly what we're saying, 2 to 3. Okay, what about theta? Well, theta goes all the way from 0 to 2 pi. So the limits are 0 to 2 pi. So this is the key part. This is the one that requires you to do a bit of thinking when we go from here to here, deciding to use polar coordinates because of the radial symmetry and all of that. Okay, and the rest is, once you do that, the rest is straightforward. 3 integral 0 to 2 pi. You can yank, the thing is, this r's, and we can separate this as a function of r times some function of theta, dr d theta. So you can separate them out and integrate them separately and multiply this out. So that gave us 195 pi over 2 as this particular integral evaluated over this. What's the practical use of this? Well, sometimes you would know that the velocity of some fluid flowing through an annulus like this, some pipe like this, okay, you would know the velocity, and the velocity would be a vector field, a velocity vector field. And when you integrate along this, about this area, velocity times area, any idea what that gives? Well, I have no idea, man. Okay, I understand. But let's think about it for a second. Velocity times area. Velocity is meter per second times area is meter square, let's say. So what do we get? Meter cube per second, or meter cube per some time interval, hour. That's nothing but flow rate. How much fluid is flowing through in a unit in 1 hour or 1 second or whatever the time is? How much fluid? Oh, 10 meter cube. In 1 hour, 10 meter cube. What is 10 meter cube? You can imagine a trough that is 1 meter in length and width is 1 meter and the height is 1 meter. That would be 1 meter cube. So if fluid were to be flowing at 10 meter cube per hour, it will fill up 10 of those troughs in 1 hour. So flow rate is a pretty important thing for both chemical engineers and civils and mechanicals, right? And this method allows us to figure out things like that, right? Isn't that fascinating? And in engineering classes, you will see this stuff. So hopefully you will remember that you learned all of this and keep these notes with you so that you can verify it if and when you need it. Okay, folks? I think I have one last problem. Whoa, what's with all this? Okay, good. So use Greens theorem to evaluate this. Oh, and it says check the orientation of the curve before applying the theorem. So we have a vector field that looks like this. Basically, this is a fancy way of saying this is P of xy and this is Q of xy. The concept is the same. And what's the curve itself? Y equals cosine x from negative pi half 0 to pi half 0. And the line segment from pi half 0 to negative pi half 0. So the book doesn't give you this figure. So I went ahead and drew this figure using GeoGebra. Basically cosine x, and x goes from negative pi half x goes from negative pi half. Oh, it had me scared a little. So cosine of negative pi, so cosine x from x equals negative pi half to x equals positive pi half, right? Negative pi half 0. So this is that curve, cosine curve. And then it needs to close the loop, and so it's from going from here to here, this line segment. Okay. What orientation is this? Notice the arrows show us that in fact this is clockwise. Absolutely imperative that you recognize that. Why? You will see that observe the orientation of closed curve is actually negative. So that means the integral that we need to evaluate, you should treat that as negative c. Okay? And this is p of x dx plus q of x p of xy dx plus q of xy dy, and because of the negative orientation we must stick a negative here. All right, and then the rest of it is straightforward. Okay, now the question becomes, well, how do we evaluate this area integral? To me it looks like it's obvious that we have to have our rectangle vertical to indicate that we would be we'll be evaluating along the x direction as a final piece, and our first integral will be along y, where y goes from y equals 0 to y equals whatever the equation of this curve is. Wait, we know the equation of the curve is cosine x. So basically 0 to cosine x would be y. And that's exactly what I have done. We go from negative pi half to pi half for the x. The negative is because of the contour being negatively oriented. Negative pi half to pi half on the outside, and the y going from 0 to cosine x of, what's with this 2x minus 2y? Well, 2x minus 2y came from finding the partial q with respect to x. Partial of this guy with respect to x is just 2x, minus partial of this guy with respect to y is 2y. Right? So that's what I did here. And the rest is straightforward. Just plug and chug, evaluate with respect to y first, and then plug the limits on y, and so on. By the way, cosine square x is 1/2 of 1 plus cosine 2x. Remember how to evaluate that. And integral of x cosine x, you got to do integration by parts. You do all that stuff, and we are in business. So this turns out to be pi halves. All right, folks. So I think that concludes this section. Just absolutely be sure to learn these concepts and how to solve problems of this kind, and you are in a good shape. So far as Greens theorem is concerned, all these, I mean, just about any section in Calc 3 is concerned, you can make it really, really complicated if you want to, or if you just learn these interesting initial concepts, I'm a happy man. All right, thanks. Bye.